We're now going to do some practice with scientific notation and proportions, different things. So we're going to start just by refreshing on changing standard form to scientific notation. So remember, we want our decimal point to come after, so we want one non-zero number in front of the decimal. So for this one, we want it to be 4.85 times 10 to the, and then we count over 1, 2, 3, 4, 5. And because this is a super small number, our exponent is negative. Now, when I say super small, anything less than 1 is considered small. So for the second one, 0.93 is less than 1. That is small, and therefore we also have a negative exponent. So I move it one place, and 9.3 times 10 to the negative first would be our answer for that one. Now, in number 3, I want to do it slightly different, because when I see the word 1,000, I think of the word 3. So I get, or I should say the number 3, 40 times 10 to the third. But that is not scientific notation, because 40 is greater than 10. So I want to move my decimal from here one spot. And 40 is big, so my exponent is going to get bigger. Because I went one spot, it gets bigger by one spot. So 4.0 times 10 to the 3 plus 1 is 4. And there would be our answer for number 3. Number 4, lots and lots of zeros here. We know we want our decimal to end up right after the 3. So 3.053 times 10 to the, and when you count all these, there should be 15 zeros, and so it's going to be times negative 16. 15 zeros and then the 3, if I typed them in correctly. I hope so. Next one. Now we have a positive. Notice how this is a big number, so 2.4, because I want one number in front of it, and 3, 6, 9, 10. So times 10 to the 10th. And number 6, we need all of those non-zero numbers. So the decimal is going to come after the 9, but I'm still going to need 8, 3, 5, 6, 3, 2, 1, 5 times 10 to the negative third, because we went 1, 2, 3. And notice how it's negative because we do have a small number. Now we're going to go the other way. We're going to go from scientific to standard. So you can see this is the same as 10 to the negative fifth, but since I typed it, I used that caret key to denote an exponent. So because it's negative, we're going to go left 5 places. So if I start with 9.34, when I go left, 1, 2, 3, 4, 5, notice all those humps are going to give me zeros. So I need a decimal to start, and then 1, 2, 3, 4, 934. So you can see how our decimal started there, and we went left 9 places. In number 8, our exponent is positive, so we're going to go to the right 4 places. So after the decimal, so this decimal's moving, there's 1 place, and then I need 3 more. So I end up with 12,000. In number 9, I've got a negative exponent, so it's going to go left. And you'll notice if we go back to number 7 real quick, we had negative 5. Notice there are 4 zeros. It will always work like that. So negative 6 means I will have 5 zeros, and then the non-zero numbers. So you will always have one less zero in front than what your exponent says when you have a negative exponent. Number 3, again, negative exponent. It's a 9, so I'm going to have 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then I have my 3. In 11, we have a positive exponent, and it's 1, so it's going to go 1 to the right, get bigger. So 71.2. And in number 12, we're going to go to the left 3 places. So 2 zeros, and then I need all of those non-zero numbers for our answer in standard form. Now we're going to do some multiplying and dividing. So remember when I'm multiplying these, right, the whole times thing, I multiply the numbers out front. So 2.31 times 2.6 gives me 6.006. And then I add my exponents. 5 plus 2 gives me 10 to the 7th. So there is my answer there. I typed this differently than what's on the paper. I apologize. So I'm going to do this one first. So in standard form, I would go 1, 2, 3, 4. Oh, shoot. Missed my 0. Let me start over. 1, 2, 3, 4, 5, 6, 7. And that would be that answer in standard form. But if you look at the paper, it's 2.31 times 10 to the negative fifth times 2.6 times 10 to the second. And that will end up with 6.006 times 10 to the negative third, which would be 0.006006. Look how different it is when all we changed there was the exponent on the first problem. So that's very different. And let's go to 14. I think I typed this one in correctly. Now we're dividing. So I'm going to take 9 divided by 1.8. And sometimes it helps to write these vertically. So if I do 9 divided by 1.8, I get 5. And then remember, we're subtracting the exponents. So negative 7 minus 2 gives me negative 9. So there's scientific notation, and then standard form, it's negative. So 1, 2, 3, 4, 5, 6, 7, 8, and then there's the 5. Number 15 is another division problem, so I divide the front numbers, and I get 2.125. And now I'm subtracting my exponents. 5 minus negative 2. 2 negatives is a positive, so that's times 10 to the 7th. So if I move my decimal 7 places to the right, I get 1, 2, 3, 4, 5, 6, 7. And there are the 2 answers for that one. Now we get into a story problem before I get to proportions. The human body uses red blood cells. You have, oh, credola. This should be, okay, I fixed my typo. 2 times 10 to the 13th, that's how many red blood cells you have. And each one is 2 times 10 to the negative 5th meters long. So if you line them up end to end, we want to know the total length. Well, total length means we want to multiply. So we're going to take 2 times 10 to the 13th and multiply by 2 times 10 to the negative 5th. So 2 times 2 is 4. Add these together and I get times 10 to the 8th. And so if you make that in standard form, 1, 2, 3, 4, 5, 6, 7, 8, there's your final answer for that one. Okay, now for a refresher on proportions, remember we cross multiply to get the proportions. So 15 times 7 gives us 105. 3 times x gives us 3x. Divide each side of the equal sign by the number in front of the x, and in this case our answer is 35. 18, cross multiply. 2x equals 36. Divide both sides by 2, x is 18. Not too bad with the smaller numbers if you understand the concept of cross multiplying. Number 19, we have some decimals. That doesn't matter, same process. 2.5x equals 14 times 9 is 126. Divide both sides by 2.5, and our x value is 50.4. Number 20. Well, at this point, you've got 50,000. So when I cross multiply, I'm going to go ahead and just write out 50,000x equals, we go this way, and I get 2,700. I'm dividing both sides by 50,000. And x will have a value of 0.054. Notice our initial direction said round to the nearest hundredth, I think. Hundredth is 2 decimal places. I look at the 4, rounds down. So really a corrected rounded answer should be 0.05. And now we are looking at number 21. Million and billion. I'm going to go ahead and rewrite this first with 25.8. Million is times 10 to the 6th. Billion is times 10 to the 9th. So when I cross multiply, I get 6 times 10 to the 9th x equals, and 3 times 25.8 is going to give me 77.4 times 10 to the 6th. So I divide by the number in front of x, which in this case is 6 times 10 to the 9th. Sorry, that 10 was a little bit janky. And x equals 12.9 times 10 to the negative third. Well, it says round to the nearest hundredth, 2 decimals, so we need to go to standard form first. So if negative 3 tells me to take this decimal and go 1, 2, 3. So I'm going to get 0.0129. Nearest hundredth is this spot, so I will just have 0.01 for a final answer here. Very exciting. 22 is very similar, so I'm going to rewrite that one first as well. 3.1, 1,000 is 3. over 1.5 times 10 to the 4th equals x over 500,000. Million is 6. So now I have 1.5 times 10 to the 4th times x, right, when I go this way. I go the other way. 3.1 times 0.5 gives me 1.55, and when I multiply, I add my exponents. So now I'm going to divide by the number in front of the x, and I end up with x equals 1.033 times 10 to the 5th, and 10 to the 5th implies getting bigger, so if I move my decimal, I get 1, 2, 3, 4, 5, and I rounded that, so if you had gone out further with your beginning number, it might be slightly different than that, but there's the basic concept. And now we're going to do a few story problems with proportions. So 23. A scientist dissolved 6 pounds of chemicals in 22 gallons of water. So we are comparing pounds to gallons. And we know our initial ratio is 6 pounds to 22 gallons. Well, then it says how many pounds, pounds is on top, should be dissolved in 24 gallons. And now that we have it set up, we can cross multiply. So let's go ahead and cross multiply and get 22x equals 144. Divide by 22, and if I round to the nearest hundredth, I should have 6.55 pounds of chemicals in 24 gallons of water. In 24, the ratio of women to men at a local college, so women to men, is 6 to 7. If there are 1,400 women, how many men should there be? Now, I know by looking, there should be more than that because the ratio is 6 to 7. So I know my answer is going to be bigger than 1,400. Now, when I cross multiply, 6x equals 9,800. Divide both sides by 6, and rounded to the nearest student, I will have 1,633 men. And that makes sense, right? That is bigger than 1,400. And the last one for this one. The line at Millennium Force, which I have ridden, shocker because I hate heights, is currently moving at a rate of 5 feet for 20 seconds. So we are talking feet to seconds. So 5 feet for 20 seconds is our initial ratio. At this rate, how long is time, so that's what's going to go on the bottom, will it take for somebody at the end of a 422-foot line? Well, now I can cross multiply. 5x equals 8,440. Divide by 5, and I end up with 1688 seconds. Well, I don't know about you, but I don't usually count that high in terms of seconds. So if I take 1688 seconds, I know there are 60 seconds in 1 minute. And so by dimensional analysis, I can take 1688 and divide by 60, and that will give me approximately 28.13 minutes. So just shy of a half hour till you will get to the front of the Millennium Force line.